So we're going to be looking at ideal gases today, and in particular some ideal gas laws. So let's say I have this container, and in this container I have a gas, and you can see that it's filled with these sort of gas particles. Now when these two gas particles collide, imagine this particle initially moving with a speed u, and then moving away at a speed v. Well, because this particle clearly has a change in velocity, it also has a change in momentum. And we know that because mv minus mu over t, there is a rate in change of momentum, so there will be a force exerted. And since there's a force exerted, well, we know that pressure is equal to force over area, so a pressure will also be exerted. So that's how gases can create pressure. Now, for some of the laws that we're going to consider in this video, we have to make a few assumptions about ideal gases. Now, the first is that the particles move at high speeds and collide elastically. So the collisions between these particles are elastic, which means they do not lose kinetic energy within these collisions. The second is that the total volume of the particles is negligible compared to the volume of the container. Now what that means is, let's say we have a container here, and in this container we have these particles. You can see that the size of these particles is almost minuscule compared to the size of a container. That's what this assumption means. It's saying that the gas takes up a negligible volume. Now the third assumption is that the time taken for each collision is negligible when compared to the time taken between collisions. Now what this means is, in a very large container, let's say we just have these two particles. These particles are going to move around randomly in some random direction, and they will do so for such a long period of time, such that when these particles do eventually collide, the time taken from when they hit is so small compared to the amount of times that they just spend roaming around freely. So that is what these three assumptions mean. Now with these assumptions, we can now go ahead and look at our ideal gas laws. Now the first one is Boyle's law. And Boyle's law states that the pressure exerted by a gas is inversely proportional to the volume of a container. And let's see why. Well, if the volume increases, there will obviously be larger time between collisions. And we know that the force is equal to the change in momentum over time. So if we have a longer time, the force exerted between these particles is less. And again, because we know that pressure is equal to force over area, if the force decreases, so does the pressure. So therefore we can say that as the volume increases, the pressure decreases. So if you were to plot a pressure versus volume graph, you'll see that it has this 1 over v relationship. And if you wanted to make it a straight line, you could actually plot pressure against 1 over volume, and that way you can get your straight line. Now the second law is Charles's law. Now Charles's law states that the volume occupied by a gas is directly proportional to the temperature of the gas. And that makes sense because when the temperature increases, we know that the particles have more kinetic energy, so the particles occupy more space. And that's because you can say that they vibrate more or move around more, so take up more space. So your volume versus temperature graph will look something like this, where your volume here is on the y-axis and your temperature here is in degrees Celsius. And now if you were to extrapolate this graph, it would actually intersect the x-axis at minus 273 degrees Celsius. And now if you were to convert this into Kelvin, we know that to convert from Celsius to Kelvin, we add 273. So the volume versus temperature graph in Kelvin looks like this. And what you can clearly see is that at 0 Kelvin, or at minus 273 degrees Celsius, particles occupy 0 volume. And 0 Kelvin, or minus 273 degrees Celsius, is known as absolute zero. And at this temperature, it is said that particles and gases occupy zero volume and exert zero pressure. And we'll see that with our next law. The final law is our pressure law. And this states that pressure is directly proportional to the temperature. And the reason for this is, well, if the temperature increases, we know that the kinetic energy of these particles increases. So that means that the rate of collisions increases. And therefore, since we're increasing the rate of collisions, the rate of change in impulse will also increase. And therefore, we exert more forces between our particles, and therefore we have a higher pressure. Now, the pressure versus temperature graphs look identical to the volume versus temperature graphs. In degrees Celsius, this graph intercepts the x-axis at minus 273 degrees C. But when you draw this graph in Kelvin, you get a graph that goes through the origin and has a straight line. So our three laws are that pressure and volume are inversely proportional to each other, and that pressure and volume are both directly proportional to temperature. And we can change any directly proportional sign into an equal sign by adding a constant. So if we were to combine all these laws together, we would see that pressure times volume over temperature is going to equal some form of constant. So let's say we had a gas here at a pressure P1, volume V1, and temperature T1, and without allowing any gas to escape or enter the chamber, we alter the pressure, the volume, and the temperature. We somehow manage to alter the pressure, the temperature, and the volume. We'll find out that the relationship between these two conditions follow this equation here. So that means that P1 V1 over T1 is equal to some form of constant, which means that it's also equal to P2 V2 over T2. So this here is our combined gas law. And this also means that PV is equal to some constant times the temperature, and we can do this by just simply rearranging our equation. And what's actually been found out is that our ideal gas equation is given by PV is equal to nRT, where P is our pressure in pascals, V is our volume in meters cubed, N is the number of moles in our system, R is a molar gas constant which has a value of 8.314, and T is our temperature in Kelvin. Now you might be thinking, well, what is a mole? So moles are a way of simply measuring how much amount of a substance we have. So the number of moles is given by the mass of that amount of substance divided by its molar mass. And you might be wondering, well, what is a molar mass? Molar masses are known values, and if you do chemistry, you might be familiar with this. If you were to look at the periodic table for, let's say, sodium, you'll have these two numbers. The molar mass for sodium is the top number, or the bigger number. So let's say you had 1 gram of sodium. If you did 1 gram divided by 23, because this here is in a unit of grams per mole, you could then find out how many moles of sodium you have. Now, if you have to use this equation, the molar mass of the substance in question will always be given to you. And this molar gas constant here is simply just a number of 8.31 that you just have to remember. It's just a constant. So now we've been introduced to the concept of moles. Let's have a look at what Avogadro's constant is. Now, Avogadro's constant is the number of particles in 1 mole of a substance. And Avogadro's constant has the value of 6.022 times 10 to the power of 23. So that means that if you have 1 mole of any substance, there'll be 6.022 times 10 to the 23 number of particles in that substance. So the number of particles given by this big letter N is equal to Avogadro's constant times by the number of moles. So here N is the number of particles, the individual particles that is, and N is your number of moles. So if we were to look at our old equation, PV equals nRT, and if we rearrange the Avogadro's constant equation, we can see that PV is equal to N over Na times RT. And we know that R is constant and that NA is a constant as well. So this here is typically a new constant. And we can call this constant K. And this here is actually the Boltzmann constant. And the Boltzmann constant K is simply the molar gas constant divided by Avogadro's number. So our second ideal gas equation can be PV equals NKT, where here capital N is the number of particles and K is the Boltzmann constant. So you can use any one of these two equations depending on the information you're given. In certain scenarios, it might be easier to use an equation in terms of moles. In certain scenarios, it might be better to use an equation in terms of number of particles. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.